Quantum nature of the electron.
At the beginning of the 19th century, the English chemist John Dalton interpreted the known experimental fact that the chemical elements react in fixed proportions, as a result of the idea that they are composed of atoms which combine with each other. In other words, an atom of an element like carbon can combine with 1, 2, 3 atoms of another element, such as oxygen, but not with √2 of an atom, for example. Dalton concluded that all atoms of a particular element are equal, and that different elements are made of different types of atoms.
One experimental procedure used to identify the type of atoms that make up an element is the analysis of the spectrum of electromagnetic radiation emitted by the element when it's heated. That is, the analysis of the emitted wavelengths or frequencies and their intensities. This can be done, for example, by use of a prism, as shown in the image. In fact, each type of atom has its own distinctive spectrum, like a fingerprint. The range of frequencies corresponding to the visible spectrum is shown in the image, each colour corresponding to a frequency. If we look at the visible emission spectra of hydrogen and mercury, we see that they are discrete. Each vertical line corresponds to an emitted wavelength or frequency.
In 1869, the Russian chemist Dmitry Mendeleev proposed a classification system of the elements, namely, the periodic table. Atoms in each of the columns are arranged from smallest to largest atomic mass and grouped with others exhibiting similar chemical properties. For instance, elements such as helium, neon, and argon in the rightmost column of the table are all noble gases, which rarely undergo chemical reactions with other elements. This ordered arrangement was nothing but a reflection of the internal atomic structure which would be experimentally discovered only a few years later.
The development of vacuum tubes by the English chemist William Crookes around the year 1870 played a key role in the study of the internal structure of the atom. On this table, we have a modern version of the Crookes tube. Let's connect it. As we can see, a bright green dot has appeared at the end of the tube. What's more, if we move a magnet towards the tube, the dot moves. This movement suggests the dot is electrically charged.
Next, let us take a closer look at the disconnected tube to find out what exactly has occurred inside. This is the glass bulb in which, in working conditions, the vacuum is produced, or a rarefied gas is introduced. The bulb includes a screen, or spherical shell, made of fluorescent material like zinc sulfide, which produces a luminous dot upon the impact of an energetic particle. Next, let's take a look at the device we use to produce electrostatic discharge. It is composed of a cathode, formed by a filament connected to its terminals, and a perforated anode, which are both connected to a high-voltage power supply. Beforehand, the filament which makes up the cathode is made to glow incandescently by connecting it to a low-voltage power supply. Finally, the tube also contains two small plates, which when connected to a low-voltage power supply, focus the aforementioned electrically charged dot by applying a suitable electric field.
Now let's see what happens step by step when we connect the tube. We begin with the low-voltage source that heats the cathode. Upon connecting it, the filament becomes incandescent. It starts to glow. If we now plug in the high-voltage source, with a voltage between 1 and 4 kilovolts, we see on the screen that a green dot has appeared. The size of this dot can be controlled with a source that feeds the focusing plates. It's clear that the presence of this dot is related to both the heating of the cathode and the high voltage applied, such that if we eliminated either of the two, the dot would disappear. Let's see an example. If we reduce the voltage to 0, the dot disappears. If we now raise the voltage again, the dot reappears. As we have already seen, the dot is electrically charged. It can be demonstrated that the movement of the dot corresponds to a set of negative charges. For positive charges, the movement would be in the opposite direction.
El desplazamiento sería en sentido contrario para cargas positivas.
We therefore conclude that there are negative charges that are accelerated from the cathode to the anode, passing through the anode and then hitting the screen. Initially, these charges were called cathode rays, and the study of their properties was a subject of interest to the most eminent physicists of the era.
In 1897, English physicist Joseph John Thomson studied the properties of the cathode rays. By analysing their displacement in a fixed magnetic field, such as a magnet, he could determine the charge-to-mass ratio. In fact, for a beam of charged particles, the radius of the curved path is related to the charge-to-mass ratio in the following manner, where B is the magnetic field strength, U the voltage applied to the cathode rays, and R the radius of the electron path. By measuring the path radius, one can determine the charge-to-mass ratio of the constituent particles of the cathode rays. J.J. Thomson identified these particles as electrons and reasoned that they must have formed a part of the material which constituted the cathode.
This suggested that the atom had internal structure. As the atom was electrically neutral, the negative charge of the electrons had to have a positive charge to counteract it. The New Zealand-born physicist Ernest Rutherford discovered in 1911 that this positive charge was concentrated in a small region at the centre of the atom, the atomic nucleus. The Danish physicist Niels Bohr proposed an atomic model in 1913 that supposed that the electrons orbiting the nucleus could only take discrete, not continuous, values for their energy. This provided a simple explanation for the atomic spectral lines. They were caused by electrons jumping between the different orbits, releasing energy in the form of photons, quanta of electromagnetic radiation. This figure shows the emission of photons corresponding to the lines of the visible spectrum of hydrogen. However, this model lacked an explanation for the fact that, according to classical electromagnetic theory, a charge in orbit, thus in constant acceleration, would constantly emit energy in the form of electromagnetic radiation. Therefore, the electron should fall into the nucleus, triggering atomic collapse.
In 1924, French physicist Louis de Broglie presented a revolutionary proposal which meant that the Bohr model could be considered consistent. He assumed that the electron could exhibit wave-like behaviour, which meant that within the atom it exists as a standing wave, thus not undergoing radiation, avoiding the atomic collapse. Furthermore, the wave-like behaviour allowed him to explain the quantification of the electron energy levels in a natural way, namely, the fact that only particular electron wavelengths, and thus energies, could generate stationary waves inside the atom. De Broglie proposed that the electron wavelength is inversely proportional to its momentum, according to the following equation.
However, if the electrons behave as waves, they should produce interference patterns when they pass through slits with widths comparable to the wavelength of the electrons. For accelerating voltages between 5 and 10 kilovolts, electrons have the wavelengths, according to de Broglie's equation, on the order of a tenth of an angstrom. Materials such as graphite, of which pencil leads are made, are formed from microcrystals of carbon atoms, in which the space between atoms is on the order of an angstrom. So, if we place a thin sheet of graphite after the anode, we should be able to see an interference pattern on the screen.
Inside the tube which we have been using is a sheet of graphite, but yet we haven't seen an interference pattern because the high power voltage was not quite high enough. Let's see what happens if we raise it. Indeed, we observe that a pattern of maxima and minima, respectively the more and less luminous regions, has appeared. The appearance of an interference pattern in which the maxima form rings is due to the arrangement of the crystalline graphite structure, depending on its possible orientations. The separation distance between the rings, on the other hand, depends on the electron wavelength. This can be demonstrated easily by looking at the effect of increasing or decreasing the voltage, as this is the equivalent to decreasing or increasing wavelength. Hence, if we raise the voltage, we can observe how the rings are brought closer together. whilst, if we reduce the voltage, the rings are once more separated further. Finally, we can see that by bringing the magnet closer, the entire interference pattern is displaced.
The electron diffraction experiment we just showed is a variant of the experiment performed for the first time in 1927. The American physicists Clinton Davison and Lester Germer performed the experiment by firing a beam of electrons at a nickel crystal. The English physicist George Thomson, son of Joseph John Thomson, performed it by firing the beam at a thin metal sheet. These experiments proved, beyond doubt, the wave-like behavior of electrons. But what type of waves are they?
In 1926, the works of the Austrian and German physicists Erwin Schrödinger and Max Born, amongst others, allowed us to obtain a rigorous mathematical description of the electrons and other physical systems. They are governed by probability functions, which in turn are represented by wave functions, which satisfy the so-called Schrödinger equation. The modulus squared of the wave function of electrons can be interpreted as the probability density of it being found at a certain position, defined by vector x at time t. The probability density also determined the interference pattern which we observed previously. These probability functions are one of the cornerstones of the quantum nature as we know it, and will be the focus of our next episode.